Imagine the most incredible machine you've ever encountered. One that can build itself, repair itself, and adapt to almost any challenge. Well, that's your musculoskeletal system. We all get the basics, bones, muscles, joints, but today we're diving much deeper. We want to reveal the hidden complexities, the constant microscopic activity within this system that most of us never really think about, even though it dictates our every single move. Our mission for you today is basically to cut through any dense textbook language. We want to give you a clear, step-by-step understanding of how your bones, joints, and muscles actually work together. We're drawing specifically from a chapter in Understanding Pathophysiology, the 7th edition by Huther and McCants, to bring you the really important stuff without getting lost in the weeds. Get ready for some genuine aha moments.
Indeed. And we'll explore the intricate structures, the cells that tirelessly build and break down tissue, the elegant mechanics of movement, and even how this entire system gracefully, or sometimes, let's face it, less gracefully, changes as we age. Our goal is really to equip you with a solid understanding, connecting the what to the why it matters in your own body and, in your overall health.
Okay, let's start with the bones then. Beyond their obvious role in structural support, what's a less known, maybe more surprising function that bones perform for our overall health?
Right, when we think bones, we usually just think structure, holding us up. But here's a real aha moment for you. Your skeleton is actually a dynamic, living factory and a chemical vault. Beyond simply giving you form and providing points for muscle attachment, bones are incredibly dynamic. They protect vital organs. Think of your skull shielding your brain or your ribs safeguarding your heart and lungs. That's crucial. But what's even more fascinating, I think, is their role in mineral homeostasis. They're constantly regulating and storing essential minerals like calcium, phosphate, magnesium, throughout your entire body. And did you know they even house hematopoietic stem cells in their marrow? Particularly in places like the skull, vertebrae, ribs, and adults, these produce your blood and immune cells. So yeah, that's a far cry from just a rigid framework, isn't it?
That's incredible. A dynamic chemical plant and shield that really changes the picture. So given all that activity, let's zoom in a bit. Beyond these dynamic cells, what is the bone actually composed of at a fundamental level?
Okay, so mature bone, it's a highly rigid connective tissue. If you could zoom way in, you'd see four main components. There are the specialized cells, we'll talk about in a sec. Then incredibly strong collagen fibers, which give it tensile strength, like rebar and concrete. You also got a gelatinous ground substance for nutrient diffusion, getting things where they need to go. And critically, large amounts of crystallized minerals, mainly calcium, giving bone its characteristic rigidity. And of course, other crucial elements like proteoglycans, glycoproteins, and specific vitamins like D and K, all playing supporting roles.
You mentioned specialized cells. What are the key players here, and what are their jobs in this bustling bone environment?
Right, the cells. Bone contains three primary cell types, and they're constantly working together, almost like a construction site crew. First, you have osteoblasts. Think of these as the bone-forming cells, the builders. They come from mesenchymal stem cells, and their job is to synthesize and secrete osteoid, that's the unmineralized bone matrix. Then they mineralize it, making it hard. They're also really important in signaling other cells, kind of directing the whole operation. Second, osteocytes. These are actually the most numerous cells in bone. You can think of them as the bone's internal sensors and its communication network. They're basically osteoblasts that have become trapped within the hardened bone matrix, living in these tiny spaces called lacunae. They sense mechanical stress on the bone, maintain the matrix around them, and play a major role in controlling both bone formation and resorption. Very important. And third, osteoclasts. These are the demolition crew. They are large, multinucleated cells that come from hematopoietic stem cells. They are the major resorptive cells of bone, meaning they dissolve old or damaged tissue to make way for new bone. They secrete hydrochloric acid and enzymes to break down bone, creating these little irregular scalloped pits called house-ship lacunae that you'd see if you looked really closely at bone undergoing resorption.
Wow, so it really is a constant construction and deconstruction project happening all the time. How do these bone-building and bone-breaking cells communicate? How do they keep things so precisely balanced?
That's where a truly elegant molecular switch comes in. It's fascinating, really. Bone's constant remodeling is tightly controlled by this delicate system involving three key players: osteoproteoglycan, OPG, RANKL, and RANK. Basically, you can think of RANKL as the signal, like an accelerator telling your body to break down bone. It promotes osteoclast formation and activation. More RANKL, more bone breakdown. OPG, on the other hand, acts like the brakes. It reduces bone loss by binding to RANKL and stopping it from activating the osteoclasts. This push-pull, this balance between RANKL and OPG, is absolutely critical for keeping your bones strong but also adaptable. If that balance gets thrown off, say with dysregulation in the system, maybe due to hormonal changes or inflammation, it can lead to conditions like osteoporosis, where the balance shifts too far towards bone resorption, towards breakdown.
Okay, that OPG or NKL system, that really paints a picture of how complex bone health is. So if the cells are the workers, what are the actual raw materials they're working with in this bone matrix? What's it made of?
Good question. The bone matrix is the extracellular framework, basically the stuff that gives bone its properties. It's primarily made of collagen fibers, specifically type I collagen. Osteoblasts synthesize these. These fibers assemble into this really clever staggered pattern. It allows mineral crystals to deposit effectively, forming a strong kind of rope-like framework that gives bone its tensile strength, its resistance to being pulled apart. Then you have proteoglycans. These are complex molecules that strengthen bone by forming these compression-resistant networks, and they also help control the transport of ions like calcium through the matrix. And you also have glycoproteins like collagen and osteocalcin. These assist in calcification, nutrient transport, and might even help facilitate bone resorption by the osteoclasts. It's all interconnected.
And then the minerals themselves, the part that makes bone hard, the rigidity.
Exactly. The final, absolutely crucial step in bone formation is mineralization. Calcium and phosphorus concentrations increase in the bone matrix, and they combine to form tiny crystals called hydroxyapatite, HAP crystals. These crystals bind really tightly to the collagen fibers we just talked about. And it's this combination, the flexible collagen and the hard HAP crystals, that provides bone with its incredible rigidity and compressive strength. It's like a natural composite material.
Okay, so if we put all these components together, the cells, the collagen, the minerals, what does this mean for the two main types of bone tissue we usually hear about? Compact and spongy.
Right. The body has two main types. Compact bone, also called cortical bone, which makes up about 85% of your skeleton, and spongy bone, or cancellous bone, which is the remaining 15%. They both contain the same basic structural elements, but they're organized very differently to serve distinct functions. It's all about architecture. Think of compact bone like the dense, highly organized steel beams of the skyscraper. It's designed for immense strength and load bearing, especially against bending forces. Its basic structural unit is the haversian system, or osteon. If you could visualize it, imagine a tiny organized cylinder. There's a central canal, the haversian canal, running longitudinally with blood vessels and nerves. Surrounding this canal are concentric layers of bone matrix called lamellae. Within these layers are tiny spaces, the lacunae, where the osteocytes live. And these lacunae are all interconnected by little channels called canalliculi, allowing nutrient exchange. This whole structure gives compact bone incredible strength. Then there's spongy bone. This is more like the internal lattice work of that skyscraper. It's lighter, less dense, more regular, but still very strong. And the spaces within it are filled with red bone marrow, where blood cells are made. Spongy bone lacks those organized haversian systems. Instead, its lamellae are arranged in plates or bars called trabeculae. These trabeculae form an irregular meshwork, kind of like a honeycomb. This design provides strength where stress patterns are more diverse, like at the ends of long bones, and it's also crucial for housing that bone marrow.
That's a fantastic analogy. The skyscraper beams versus the internal lattice work. Yeah. Okay, so with this incredible architecture, how do bones keep themselves in top condition day to day? Or, heal when something more serious happens, like an injury?
Right, bones aren't static once they're formed. The internal structure is constantly maintained through a process called remodeling. This happens throughout life, carried out by clusters of bone cells called basic multicellular units, or BMUs. It's essentially a three-phase process. First, there's activation. Some kind of stimulus, maybe hormones, maybe physical stress, maybe microdamage activates precursor cells to form osteoclasts. The demolition crew gets called in. Second, resorption. The osteoclasts attach to the bone surface and start digesting or resorbing old bone, creating these little resorption cavities. Third, formation. Then the osteoblasts, the builders, move into those cavities. They secrete osteoid and then mineralize it, laying down new bone in successive layers, filling up the hole. This whole cycle, activation, resorption, formation, takes about 4 to 6 months in humans. It's this continuous quality control system. It allows the skeleton to adapt to mechanical loading, repair tiny damages we get all the time, and also regulate calcium levels. Now, for larger injuries like a fracture, bone healing follows specific stages. It's similar in some ways to how soft tissue heals, but the end result is new bone, not scar tissue. 1. Hematoma formation. Right after the break, blood vessels rupture and a blood clot, a hematoma, forms at the injury site. This happens within hours. 2. Procallus formation. Within days, osteoblasts and other cells start forming new tissue within that hematoma. 3. Callus formation. Over the next few weeks, this develops into a soft callus, kind of like a bridge made of fibrous tissue and cartilage connecting the broken ends. 4. Replacement. Then those basic multicellular units get to work replacing the soft callus with actual woven bone, first spongy, then compact. This makes the callus hard. 5. Remodeling. Finally, over months to years, the bone is remodeled. The excess callus is removed, and the bone gradually returns to its original size and shape, responding to the stresses placed on it. And an interesting point. Spongy bone actually tends to heal faster than compact bone because it has a better blood supply and more surface area for remodeling.
That healing process is remarkable.
Mm-hmm.
Okay, so we've seen how dynamic and busy bones are. But for all that incredible structure to translate into actual movement, these bones need to connect and articulate, right? That brings us seamlessly to our next crucial component, joints. What's their fundamental role in making us truly mobile creatures?
Exactly. Joints, or articulations, are simply where two or more bones meet. Their primary function is this really delicate balance between providing stability and allowing mobility for the skeleton. Generally speaking, joints that are designed mainly for stability tend to have simpler structures, whereas those that permit a lot more movement are usually more complex in their design, and the degree of movement they permit is actually one of the key ways we classify them.
Okay, so how do we classify these incredibly diverse connectors in our body? What are the main categories?
Well, we can classify them in two main ways. First, based on how much movement they allow. You have synarthroses. Think syn, as in together. These are immovable joints. The classic example is the sutures in your skull, where those flat bones are bound tightly together by a thin layer of fibrous tissue. No movement there. Then amphiarthroses. Amphi meaning on both sides or around. These are slightly movable joints. Good examples are the intervertebral discs in your spine or the pubic symphysis. They're united by pads of fiber cartilage that allow a little bit of give. And finally, diarthroses. Di suggesting separation. These are the freely movable joints. These are most of the joints we typically think of when we talk about movement, like your knee, your shoulder, your hip, your fingers. The second way we classify joints is by the type of connective tissue that holds the bones together. Fibrous joints. Here, bone is united directly to bone by dense, fibrous connective tissue. They generally allow very little, if any, movement. Examples include those skull sutures we mentioned, also syndesmoses, like the joint between the tibia and fibula down near your ankle, and gomphoses, which are basically the pegs that hold your teeth in their sockets. Cartilaginous joints. In these, bones are united by cartilage. There are two types here. Symphyses use fiber cartilage pads, like the pubic symphysis and those intervertebral discs again. These act as great shock absorbers. Synchondroses, on the other hand, use hyaline cartilage, like the joints between your ribs and your sternum. These allow slight movement, which is important for breathing.
Right. And the most complex and mobile of these, the synovial joints, the diarthroses, what's the secret to their smooth, fluid movement?
Ah, synovial joints. Yes, they are indeed the most movable and also the most complex. If you could peek inside, say, your knee joint, you'd see the ends of the two bones involved. Each bone end is covered with smooth articular cartilage. The whole thing is encased in a tough, fibrous joint capsule. Lining the inside of this capsule, except over the cartilage surfaces, is a delicate synovial membrane. This membrane is key because it secretes synovial fluid into the joint cavity, which is that potential space between the articulating bones. This synovial fluid is amazing stuff. It acts as a super efficient lubricant, reducing friction to almost zero. It also nourishes the articular cartilage, which doesn't have its own blood supply, and it contains cells, like phagocytes, that help clean up any debris within the joint space, keeping things running smoothly.
Okay, tell me more about this articular cartilage. You said it's vital. What's its job exactly, and how is it built for that role?
Articular cartilage, which is usually hyaline cartilage in these joints, is absolutely vital for smooth, pain-free movement. Its main jobs are to reduce friction between the bones, allowing them to glide almost effortlessly, and to distribute the weight-bearing forces across the joint surface, acting like a shock absorber. It's composed of specialized cells called chondrocytes, embedded within an extensive intercellular matrix. This matrix is mostly water, but its key structural components are type 2 collagen fibers and large molecules called proteoglycans. This cartilage is actually built like a sophisticated natural composite material. If you look at its structure, the collagen fibers are strategically arranged. Near the surface, they run parallel to the joint, creating a smooth, dense protective mat for gliding. In the middle layer, they're arranged more tangentially, almost randomly, allowing the cartilage to deform slightly and absorb shock. And in the deepest layer, the fibers run perpendicular to the surface, anchoring the cartilage firmly to the underlying bone at a specialized calcified layer called the tite mark. The proteoglycans within this collagen network attract and hold water, giving the cartilage its stiffness and resilience, and helping regulate fluid movement under pressure. It's really nature's most advanced engineering for smooth, low-friction movement.
Wow, the structure is incredible. So with all this intricate design, what does this mean for the actual range and types of movements our synovial joints can perform?
Because of this structure, the smooth cartilage, the lubricating fluid, the capsule holding it together, synovial joints allow a huge range of movements. We describe these based on the axis of motion. Some are uniaxial, meaning they move in one plane, like your elbow acting as a hinge. Others are biaxial, moving in two planes, like your wrist allowing bending and side-to-side movement. And some are multiaxial, allowing movement in multiple planes, like the ball and socket joints of your shoulder and hip, which permit rotation and movement in all directions. These movements can be circular, like circumduction, or angular, like flexion and extension. This versatility enables everything from simple walking to the most complex athletic maneuvers.
Okay, this is great. With our structural framework, bones, and their flexible connectors joints understood, it's definitely time to talk about the engines, the parts that actually power all this movement, our skeletal muscles. How did these incredible workhorses actually translate a thought, an intention into physical action?
Skeletal muscles, yeah, they're incredibly sophisticated biological machines. They make up about 40% of an adult's body weight, which is substantial. And they consist of literally millions of individual muscle fibers that contract and relax to produce movement. Each whole muscle, like your biceps, for example, isn't just a random bundle of fibers. It's a highly organized organ. It's wrapped in layers of connective tissue, collectively called fascia. Think of this fascia as specialized packaging. It protects the muscle fibers, ensures they all pull together efficiently, and crucially, it extends beyond the muscle belly to form the tendon, which attaches the muscle to the bone. There are three main layers of this connective tissue. The epimysium is the outermost layer surrounding the entire muscle. Inside that, the paramysium divides the muscle fibers into bundles called fascicles. And finally, the delicate endomysium surrounds each individual muscle fiber within a fascicle. This organization is key to generating coordinated force.
So the muscle is beautifully organized, from the whole muscle down to the individual fibers. That makes sense for transmitting force. What's the fundamental functional unit that actually gets these muscles moving? The command unit, so to speak.
That would be the motor unit. It's really the fundamental functional unit of the entire neuromuscular system. A motor unit consists of one specific anterior horn cell that's a nerve cell in the spinal cord, its long axon extending out to the muscle, and all the individual muscle fibers that this single axon innervates or connects with. When that anterior horn cell fires an electrical impulse, the signal travels down the axon, and all the muscle fibers within that motor unit contract simultaneously as a single entity. It's an all or none response for that unit. Now, the innervation ratio, meaning the number of muscle fibers controlled by a single motor axon, is really significant functionally. In large muscles used for posture or powerful movements, like your calf muscle, a single axon might innervate thousands of fibers, a high ratio. This promotes endurance and prevents fatigue, as not all units fire at once. But in muscles needing fine control, like the tiny muscles that move your eyes or control your larynx for speech, the ratio is very low, maybe just 2 or 3 muscle fibers per axon. This allows for incredibly precise, graded movements. Muscles also contain these really sophisticated sensory receptors embedded within them. Muscle spindles lie parallel to the muscle fibers and are sensitive to stretch. They send feedback about muscle length and the rate of change in length. And Golgi tendon organs, which are located in the tendons, respond to tension or force generated by the muscle. These receptors provide vital, real-time feedback to the central nervous system. They help maintain muscle tone, coordinate movement, protect against overstretching or excessive force, and initiate crucial reflexes like the muscle stretch reflex, that knee-jerk reaction the doctor tests.
Okay, so we have these motor units controlling bundles of fibers and sensors providing feedback. But what makes up an individual muscle fiber itself? Is it just one long cell, or is it more complex inside?
Each muscle fiber is indeed a single, very long, cylindrical muscle cell. They can be quite large, actually. And inside each fiber are bundles of myofibrils. These are the functional subunits, the actual contractile elements of the muscle cell. Muscle fibers are fully formed around the time of birth from precursor cells called myoblasts. We generally don't make new muscle fibers after that. But, and this is crucial for muscle health and repair, we have satellite cells. Think of these as your muscle's dormant reserve team, or stem cells. They sit quietly on the surface of muscle fibers. When a muscle is injured or needs to grow stronger, these satellite cells get activated. They multiply and differentiate, fusing with existing fibers to repair damage or contribute to hypertrophy growth. They are absolutely vital for muscle growth, maintenance, and recovery after exercise or injury.
That's fascinating about the satellite cells. Now, I've heard about different types of muscle fibers, red and white, slow twitch and fast twitch. I feel like I can almost feel the difference sometimes after, say, a long run versus a quick sprint. Can you break down how they differ?
Absolutely. That difference you feel is real.
Mm.
We have two main types of skeletal muscle fibers, and most muscles contain a mixture of both, though the proportions vary depending on the muscle's function. Type I fibers, often called red or slow twitch fibers, these tend to be smaller in diameter. They're rich in myoglobin, which stores oxygen, giving them the red color, and packed with mitochondria, the powerhouses of the cell. They rely primarily on aerobic oxidative metabolism, using oxygen to generate ATP efficiently. As the name suggests, they contract relatively slowly but are highly resistant to fatigue. They're perfect for maintaining posture, endurance activities like long-distance running, or any sustained low-intensity effort. Think of the postural muscles in your back or the soleus muscle in your calf. Type 2 fibers, often called white or fast twitch fibers, these are generally larger in diameter. They have less myoglobin and fewer mitochondria compared to type Y. They rely more on anaerobic glycolytic systems, breaking down glucose without oxygen for rapid energy transfer. These fibers contract very quickly and forcefully, but they fatigue much more readily. They're used for short, intense bursts of activity, like sprinting, jumping, or lifting heavy weights quickly. The muscles that move your eyes are almost exclusively type 2, allowing for those rapid saccadic movements. There are subtypes within type 2 like Ia and Ialiscus or Ibid with slightly different characteristics, but the main distinction is fast, powerful, but fatigable.
Okay, that makes a lot of sense, slow and steady versus fast and furious. So let's get down to the nitty-gritty. How does a muscle actually contract at the molecular level? What's the mechanism?
Right, the actual contraction. It's a beautiful molecular dance, often explained by the sliding filament theory or crossbridge theory. It happens in four main steps within each sarcomere, which is the basic contractile unit of a myofibril. 1. Excitation. It starts with a nerve impulse arriving at the neuromuscular junction. This signal spreads along the muscle fiber membrane, the sarcolemma, and dives down into the fiber via little channels called transverse tubules, T-tubules. 2. Coupling. This electrical signal traveling down the T-tubules triggers the release of massive amounts of stored calcium ions, Ca2+, from the sarcoplasmic reticulum, which is like a calcium reservoir wrapped around the myofibrils. Calcium floods into the sarcoplasm, the cytoplasm of the muscle cell. 3. Contraction. Now this is the key part. Calcium binds to a protein called troponin, which sits on the actin-thin filaments. This binding causes another protein, tropomyosin, which normally blocks the binding sites on actin, to shift out of the way. With the binding sites exposed, the heads of the myosin-thick filaments can now latch onto the actin filaments, forming what we call cross bridges. Think of the myosin heads like little oars. Using energy from ATP, these myosin heads pull the actin filaments inward, towards the center of the sarcomere. This causes the sarcomere to shorten, and since all the sarcomeres shorten together, the entire muscle fiber contracts. This repeated cycle of myosin binding, pulling, detaching, and rebinding is the famous cross-bridge cycle. 4. Relaxation. When the nerve signal stops, calcium ions are actively pumped back into the sarcoplasmic reticulum using ATP. As calcium levels drop, troponin and tropomyosin shift back to their original positions, covering the actin binding sites. The myosin heads detach, the cross bridges break, and the sarcomere, and thus the muscle fiber lengthens and relaxes.
That molecular dance is incredible. And you mentioned ATP multiple times. It sounds incredibly energy intensive. How does the muscle fuel such a demanding process, especially considering those different types of activity, short bursts versus long endurance?
You're absolutely right. Muscle contraction is extremely energy hungry. Skeletal muscle requires a constant, ready supply of ATP, adenosine triphosphate, the main energy currency of the cell, and also phosphocreatine, PCR, which acts like a small, immediate backup energy reserve. For very brief, intense activity like the first few seconds of a sprint or a heavy lift, lasting maybe under 5 seconds, the muscle uses the small amount of ATP it has stored directly, along with quickly converting phosphocreatine back into ATP. This is immediate anaerobic power. For slightly longer bursts of intense activity, lasting maybe up to a minute or two, the muscle shifts primarily to anaerobic glycolysis. It rapidly breaks down stored glycogen, muscle sugar, and glucose from the blood without needing oxygen. This is fast, but it's less efficient than aerobic metabolism, and it produces lactic acid as a byproduct, which contributes to that muscle burn and eventually fatigue. For sustained, strenuous exercise or even moderate activity lasting more than a couple of minutes, the aerobic pathways kick in fully. Using oxygen delivered by the blood, the mitochondria efficiently break down glycogen, glucose, and importantly, fatty acids mobilized from fat stores to produce large amounts of ATP. This can sustain activity for much longer periods. When the energy demand outstrips the oxygen supply or fuel availability, the system can't keep up. You start relying more on anaerobic glycolysis again, lactic acid accumulates, ATP levels might drop slightly, and you accumulate an oxygen debt, the extra oxygen needed after exercise to restore everything back to normal. And that's when fatigue really sets in, forcing you to slow down or stop.
That interplay of energy systems is fascinating. Okay, so we know how individual fibers contract and get energy. How does the central nervous system coordinate all these muscle units to produce just the right amount of force for different tasks? Lifting a feather versus lifting a heavy weight.
Excellent question. The central nervous system has very clever ways to grade or control muscle force precisely. It does this mainly in two ways. First, by recruiting more motor units. For a very light task, only a few motor units might be activated. As you need more force, the brain recruits progressively more motor units, particularly activating the larger, more powerful fast-twitch units for maximal efforts. This is called motor unit recruitment. Second, by varying the firing frequency of the active motor units. A single nerve impulse causes a single twitch in the muscle fibers of a motor unit. If impulses arrive slowly, the twitches are separate. But if the nerve fires more rapidly, the twitches start to summate, producing more force. If the firing frequency becomes very high, the muscle fiber doesn't have time to relax at all between stimuli, and the contractions fuse together into a sustained maximal contraction called physiologic tetanus. This generates much more force than a single twitch. So by adjusting both the number of motor units firing and the rate at which they fire, your brain can fine-tune muscle force across an enormous range. And of course, other factors influence efficiency too, like the muscle fiber type composition, fast twitch for rapid force, low twitch for sustained, the innervation ratio we talked about, muscle temperature, warm muscles contract more efficiently, and even the overall shape and leverage of the muscle. For instance, muscles with a larger cross-sectional area can generally develop greater contractile forces.
Okay, recruitment and firing rate. That makes sense. And what about the different types of contractions we experience? Like holding something still versus actively lifting or lowering it.
Right. We generally talk about two main types of dynamic contractions plus a static one. Isometric, static contraction. Iso means same, metric means length. Here, the muscle develops tension, but its length doesn't change. Think about pushing against an immovable wall or holding a heavy bag perfectly still. The muscle is working hard, generating force, but the joint angle isn't changing. Your muscles are firing, but the limb doesn't move. So when you're holding a plank, for instance, your core muscles are contracting isometrically. Dynamic, isotonic contraction. Iso means same, tonic means tension, though tension actually fluctuates a bit. Here, the muscle maintains a relatively constant tension as it changes length and moves a load. This type has two phases. Concentric contraction. This is when the muscle shortens as it contracts. Think of lifting a weight during a bicep curl. Your biceps muscle is shortening as it overcomes the resistance. This is usually the lifting phase of an exercise. Eccentric contraction. This is when the muscle lengthens while still under tension. Think of slowly lowering that weight during the bicep curl. Your biceps is still contracting to control the descent, but it's lengthening against the resistance. Eccentric contractions can actually generate more force than concentric ones, and they're often the ones that cause more muscle damage and that delayed onset muscle soreness, DOMS, you feel a day or two after a hard workout. And it's important to remember muscles almost always work in coordinated groups. You have the agonist, or the prime mover, which is the muscle primarily responsible for a given movement. Then you have the antagonist, which is the muscle that opposes the action of the agonist. When the agonist contracts, the antagonist typically relaxes to allow smooth movement. Think of bending your elbow again. Your biceps is the agonist, it contracts to flex the elbow, and your triceps on the back of your arm is the antagonist, it has to relax. When you straighten your elbow, the roles reverse. Your nervous system automatically coordinates these actions.
Perfect. Okay, one last piece of the puzzle before we talk about aging. What about the other crucial soft tissues we often hear mentioned alongside muscles and bones? Tendons and ligaments. What are their distinct roles?
Good point. They're absolutely essential. Tendons are tough cords of fibrous connective tissue that attach muscle to bone. Their main job is to transmit the force generated by muscle contraction to the bone, thereby producing movement. They attach to bone at a specialized junction site called an enthesis. Tendons also act a bit like biological springs, storing and releasing elastic energy, which can improve the efficiency of movement, like in running or jumping. Ligaments, on the other hand, are also strong bands of fibrous connective tissue, but they attach bone to bone. Their primary role is to stabilize joints, holding the bones together and limiting excessive or unwanted movement, guiding joint motion. Both tendons and ligaments are primarily composed of dense, regularly arranged collagen fibers, mostly type I, and specialized fibroblast cells. Ligaments typically contain a bit more elastin than tendons, giving them slightly more flexibility. What's really fascinating, and a challenge clinically, is the complex structure of that enthesis, the attachment site where tendon or ligament integrates into bone. It's a very specialized zone that transitions gradually from fibrous tissue to fibrocartilage to mineralized fibrocartilage to bone. This complexity makes healing these tissues after injury, like an ACL tear or rotator cuff tear, a significant challenge in rehabilitation. Researchers are actively working on engineering suitable biodegradable scaffolds to try and replicate this complex structure and improve repair outcomes.
That complexity at the attachment site makes sense for why those injuries can be so tricky. Okay, so we've explored this system's incredible design and function from bone cells all the way to tendons. What does this all mean for us as we navigate life? How does aging typically affect this incredible, dynamic musculoskeletal system?
Right, aging brings significant, though gradual, changes across the entire musculoskeletal system. It's a natural part of the life process, but understanding it is key. Let's start with bones. As we age, bones tend to become less dense, less strong, and consequently more brittle. The remodeling cycle we talked about, that balance of breakdown and formation, slows down. Resorption might slightly outpace formation, leading to a net loss of bone mass. Mineralization also decelerates. Women typically experience a period of accelerated bone loss, particularly in the years around menopause, primarily due to the decrease in estrogen, which normally helps restrain osteoclast activity. This significantly increases the risk for osteoporosis. Men also experience age-related bone loss, though it generally starts later and progresses more slowly than in women. We also often see a decrease in height with age, partly due to changes in intervertebral discs and vertebral bodies. Now, joints. Changes happen here too. Articular cartilage tends to become more rigid, more fragile, and more susceptible to fraying or damage. This is due to changes in the collagen structure, a decrease in water content, and reduced concentrations of those important proteoglycans. Basically, it loses some of its resilience and smooth gliding properties. Ligaments and tendons also tend to shrink and harden somewhat with age, leading to decreased flexibility and range of motion in joints. Those intervertebral disc spaces in the spine, for example, often decrease in height and lose water content, contributing to stiffness and that loss of overall body height. And muscles. We see a phenomenon called sarcopenia, which is the age-related loss of skeletal muscle mass, strength, and function. This typically begins gradually around age 50, but the decline often becomes more noticeable after age 70 or so. What's happening underneath? There's often a preferential decrease in the number and size of type 2 fast-twitch muscle fibers. Mitochondrial function might become less efficient. There can also be a reduction in the number of motor units, and the remaining ones might get larger but potentially less efficient. But here's the really hopeful and important part. Despite these age-related changes, the fundamental regenerative capacity of muscle tissue, thanks to those satellite cells and its ability to respond and adapt to exercise, its trainability, seem to remain largely normal even into advanced age. This strongly emphasizes that maintaining physical activity and good nutrition is absolutely key to mitigating sarcopenia and preserving function as we get older.
That's a crucial point.
Yeah.
So while some decline might be, well, inevitable as part of aging, it sounds like we still have a lot of agency. We can definitely influence how well our musculoskeletal health holds up throughout our lives.
Exactly. Understanding these changes isn't meant to be discouraging. Instead, it helps us appreciate the system's inherent resilience and underscores the profound importance of things like regular weight-bearing exercise, resistance training, adequate calcium and vitamin D intake, and overall good nutrition throughout our entire lives. We can actively support this amazing system.
Wow, what an incredible deep dive, truly, into the musculoskeletal system. We've covered so much ground, from the intricate dance of bone cells remodeling our skeleton, to the elegant mechanics of how our joints allow movement, the powerful yet precise actions of our muscles, and how it all gracefully, or sometimes, less gracefully evolves with age. We really hope this journey through the bones, joints, and muscles, drawing from that Understanding Pathophysiology chapter, has given you a much clearer picture of the incredible biological engineering happening inside your own body right now. From the microscopic world of osteoclasts and sarcomeres, all the way up to the macroscopic strength and movement of your skeleton, it's truly a system of constant renewal, adaptation, and potential.
Absolutely. And if we connect this all back to the bigger picture, it just highlights how profoundly our everyday function, our ability to move, our independence, and ultimately our overall quality of life depend directly on the health and integrity of this single, incredibly complex system. So maybe this raises an important question for you, our listener, to ponder. Knowing what you now know about the constant remodeling, the repair capacity, and the adaptability of your bones and muscles, even with aging, how might that influence your own approach to movement, to exercise, to health in your own life moving forward?
That's a great thought to leave everyone with. Thank you so much for joining us on this deep dive. Keep learning, keep moving, stay curious, and we'll catch you on the next one.